I'm back. Okay, so here we go. Right now what we're going to talk about is applications of the triple integral, specifically volume right now. We're going to talk about a couple of other things and another application. So we're going to do a couple of applications. So to find the volume of a general solid bounded region E, we do pretty much the same thing that we've done previously, and we integrate 1. So the function 1 over our region dV. Let's do an example. We want to find the volume of the region that lies behind the plane x plus y plus z equals 8, and in front of the region in the yz plane that's bounded by z equals 3/2 square root y and z equals 3/4 y. So thankfully, we're given the region D this time, so we can easily sketch it. And the intersections of the 3 regions, thank you, Maple. So this is the region D to the left and the intersection of the 3 regions to the right. So let's figure out what the limits of the variables. So using the left-hand picture for D, we see that y ranges from 0 to 4, and z is between those 2 curves. So z is between 3/4 y and 3/2 square root of y. Of course, we didn't necessarily have to do it that way, but what about now x? So now we just go back. Our plane is x plus y plus z is equal to 8. So x is equal to 8 minus y minus z. And so we could see from our graph, first of all, let me see. So lies behind the plane and in that region. So we see that x is going to be greater than or equal to 0. Just by looking at our picture, right, in that region. And it's bounded by the plane, 8 minus y minus z, because we solved here. So that's the deal. All we have to do now is set up our triple integral and solve. So our volume is the triple integral of 1, right? So we're going to have the integral from 0 to 4, the integral from 3/4 y to 3/2 square root of y, and the integral from 0 to 8 minus y minus z of, well, 1. Now let's see, we've got dx, dz, dy. Okay, so that's going to give me the integral from 0 to 4, integral from 3/4 y to 3/2 root y of, let's see, we have going to z, and evaluate at the limits. I'm sorry, let me rephrase that. We don't have z, we have x. So we're going to have the integral from 0 to 4, the integral from 3/4 y to 3/2 root y. Plugging in our limit, we get the function 8 minus y minus z. And next, we're going to integrate with respect to z. So that's going to give us the integral from 0 to 4. We're going to have 8z minus yz minus 1/2 z squared. And we need to plug in our limits. And then we can finally integrate with respect to y. Due to space constraints, I'm just going to actually plug them in. So we're going to get 12 root y minus 57 over 8y. Minus 3/2 y to the 3/2 plus 33 over 32 y squared dy. At least that's what Maple gave me, or whatever I used to calculate this. And finally, we integrate with respect to y, so we get 8y to the 3/2 minus 57 16ths y squared. Now minus 3/5 y to the 5/2 plus 11 over 32 y cubed, evaluated at our limits. And that's going to give us, after plugging it into a computational device, 49/5. Phew. So as you can see, these integrals can be quite entertaining, and it is helpful to use a computer assist for some of this stuff. Now, of course, as I mentioned, I didn't have to do my integral that way. We could change the order of integration, and sometimes that's more convenient. And that follows in exactly the same way as it did for integrals in 2 dimensions. Also, sometimes we might find it convenient to use polar coordinates to compute integrals. And again, pretty much the same as for integrals in 2 dimensions. Now, your book has some examples also, so please look at the book for some of these. Examples are really nice to look at. Okay, one more application of integrals, or triple integrals. Again, the average value of a function. So if we are given a function f of x, y, and z that is integrable over a solid bounded region E having volume, we'll just say v of E, then the average value of f, which we'll denote by f, so av, is given by, well, you can probably guess now that we're going to take 1 over the volume times the integral of our function over that region. As a note, right, the volume is how we just calculated volume. So our volume is going to be given by just computing the integral over the region of 1. So let's do an example. Let's find the average value of the function f of x, y, and z being x times y times z over the solid here, which happens to be the box 0, 1 by 0, 2 by 0, 3. So fortunately, this is a rectangular prism. So the volume of our region is simply right length times width times height. So we're going to have the 1 minus 0 times 2 minus 0 times 3 minus 0, also known as 6. Excellent. So therefore, we're going to have that the average value is going to be 1/6 times the integral, and you can choose whatever order you want. I'm just going to do 0 to 1, 0 to 3. My function is x times y times z, and I'm going to do dz, dy, dx. So I'm going to integrate with respect to z first, y second, and x third. So we'll do z first. So I'm going to have 1/6 times the integral 0 to 1, 0 to 2. So when I'm integrating with respect to z, I'm going to get 1/2 xyz squared from 0 to 3, plugging in our limits. That's going to give us 1/6, 0 to 1, 0 to 2 of 9/2 xy dy dx. So then I'm going to integrate with respect to y first. That's going to give me 1/6 integral from 0 to 1. I get 9/4 xy squared. Plug in the limits. So I'm going to get 1/6 integral from 0 to 1 of 9x dx. And finally, that's going to give me 1/6 times 9/2 x squared. Evaluating at the limits, I'm going to get 1/6 times 9/2, which is, after we do some reduction, is going to give me 3/4. So our answer is 3/4. And oh, look, some suggested exercises for you to get some additional practice. So I encourage you to do those. Next time, we are going to talk about triple integrals in cylindrical and spherical coordinates, which, well, we're going to actually break that up into 2. We'll do cylindrical first and then spherical. So that's where we're heading next. Have a great day, everybody.